So let us start. Got it? So we'll be discussing the vertex flow. So in case if there are any vertices, so vertices means the curls, right? So if there are any curls, that will be modeled as the complex potential of, so the complex potential of a vertex will be W is equal to Ik by 2 pi times of log Z minus Z1 or Z. So this is how actually we'll be modeling the complex potential of any vertex, right? So in this vertex flow, now actually there are the questions that are going to be coming. In case of vertex flow, I said that it is very, very complex in nature, right? So let us solve few problems on that, so which were given in the previous years of UPSC. Then actually see how we can solve this kind of problems. So this is the only information that is needed. I'll just summarize what we have discussed. So W is equal to Ik by 2 pi times of log of Z minus Zi is nothing but the complex potential of any vertex. Now, the vertex actually will create the circular flow of the water there. Now, this circular flow of the water, if there are two different vertices that are present. Now, let us say this is one place where the curl is produced. That means there is a vertex that is here, and then the strength of the vertex is nothing but the K. So that means how much ability it is having to rotate the fluid there. That's what we call as the strength of the vertex, and that's what actually is represented with the letter called K. So where K is the strength of the vertex. Right? So K is the strength of the vertex. Now actually let us say this strength is, let us say, K. So K is nothing but the anti-clockwise rotation of the circular. So this is plus K. Suppose if it rotates in the opposite direction, this is minus K. So this is how actually we will represent. That is, a curl can be clockwise or anti-clockwise direction. Usually the standard convention is anti-clockwise we treat as positive and clockwise we treat as negative. Now this curl which is rotating at this particular point, and there is one curl actually which is rotating at this particular point. Now here one important concept that you need to understand is, suppose if you want to take one fluid element at this particular point, that particular fluid element is getting influenced by both the vertices. So this is with plus K and this is with minus K. If there are multiple vertices, then all the vertices together will influence this fluid particle to move from there. So here actually the potential, the complex potential at this particular point is nothing but, because of this it will be Ik by 2 pi times of log Z minus, let us say this is Z1 and this is Z2, then Z minus Z1. So because of this it will be minus Ik by 2 pi times of log Z minus Z2. So this is the total complex potential of the fluid particle at this particular point, and this is known to everybody. So that is, this fluid potential at this particular point will decide, this W is nothing but phi plus I psi, where this is the scalar potential and this is the streamline. So this is the streamline function, this is the scalar potential function. Once we got to know this, then actually, so we can find out the velocity, that is U. So minus U plus IV is nothing but dW by dZ. So this is what actually we have already proved that. So this one you need to know, this one you need to know, and this one you need to know to solve any kind of problems that you come across in case of vertex flow. These are the only three important principles that are there, right? So these are actually anyway the fundamentals, and this is the new thing, that's what you learn now. And then one more important concept that you need to understand to solve vertex problems is, suppose if there is a fluid particle at this particular point, this is getting influenced by both the vertices. But what if there is a fluid particle at this particular point? So will it get influenced by both the vertices, or it will get influenced by only one? If yes, then which one? Got it? Understood, Keshav? The question what I asked is, So if there is a fluid particle at this particular point itself, that is where the first vertex is there. Now, this vertex is getting influenced by this vertex and this vertex together, or only with this one, or only with this one. So it's not. So that's exactly what you need to understand. Here, outside the vertex filament, the fluid particle is getting influenced by both the vertices, but within the fluid part, within the vertex itself, the point on this particular point, right? So the fluid particle at this particular point is getting influenced by only because of this vertex, not because of this vertex. If there are 100 different vertices are there, now the fluid particle within one particular vertex will get influenced by all other 99 vertices, but not with the one which is there itself. Got it? So this is getting influenced by, because this will try, so this vertex will try to move this particular particle in this direction. Got it? But this is at the middle, that is at the center, which is at the stable condition. Now the influence is just because of this one, not because of this one, because this itself makes the rotation there itself. Got it or not? Understood? This one very, very important concept while solving the vertex related problems. So suppose if you want to find out the velocity of the fluid particle at this particular point, you have to use the total complex potential. But if you want to use the complex potential at this particular point, you have to subtract the complex potential of this one from the total complex potential. That is, exclude this one and then form the complex potential equation because of all other vertices together there. This concept you need to understand very clearly. Got it? Any questions on this? Okay, great. Now, based on this understanding, we will solve some problems. Okay, note down this problem. This was given by UPSC already some time back. If n rectilinear vertices, if n rectilinear vertices of the same strength K are symmetrically arranged, of the same strength K are symmetrically arranged as generators of the circular cylinder. Circular cylinder of radius A in an infinite liquid. Of radius A in an infinite liquid. Prove that the vertices will move round the cylinder uniformly in time uniformly in time 8 pi square a square by n minus 1 times of k, and find the velocity at any point of the liquid. at any point of the liquid. So this is what actually given, I think somewhere around 2010 or 2011 or so. So this is in if n rectilinear vertices means I told you it will have the same axis of rotation. So those are called as the rectilinear vertices. Suppose whatever the vertices we see usually those are rectilinear vertices only, because if you see from the top, right, so you will find the circles there itself like this. So both are having the same axis. So this axis actually is nothing but the rectilinear vertices. So axis may be top or bottom, it doesn't matter, but actually both are exactly on the same plane. Got it? So this is what we call as the rectilinear vertices. Now n such kind of rectilinear vertices are there. Now if there are n such kind of rectilinear vertices are there, all those are distributed in such a way as generators of the circular cylinder of radius a. That means there is a circular cylinder. So this is a circular cylinder. Now on this particular circle there are vertices. Like this, actually the vertices are getting distributed. This is how actually the vertices are distributed, and there are n such kind of vertices are there. Let us say each of strength of magnitude k. So let us say this is the strength of magnitude k. Now all are having the same kind of rotation like this. Got it? So same strength k, all are symmetrically arranged as generators of the cylinder of radius a in an infinite liquid. Prove that the vertices will move around the cylinder uniformly in time 8 pi square a square by n minus 1 times of k. So these vertices, right? Suppose if these kind of vertices are there, now will they stay as it is, or actually will it move from one location to another location? I hope you understood the question. So these vertices, will it stay as it is and rotate there itself, or actually will it move in some manner? Can somebody answer the question? They will move, right? Now actually for this kind of scenario, right, so these vertices will move randomly, but actually the arrangement of this kind of vertices will rotate in a circular fashion with radius a only. That means all these vertices will try to rotate like this. So this is like actually Earth is rotating about itself, and then it is rotating around the sun itself, right? So both are there. That means let us say if this is the sun and this is the Earth, it will rotate on its own and it will try to rotate in the entire circle. So all these vertices together will try to rotate in this particular manner. Got it? Understood or not? Now actually what he asked was, so with what velocity these things will move? That is one question. And then if you take one vertex, right, so that particular vertex, so with what velocity it is trying to move? That is one question. And another question, if I take a fluid particle at this particular point, with what velocity that fluid particle will get moved? So both the questions are there. Now, if this vertex is moving around the circle, then, so he asked us to prove that it will take 8 pi square a square by n minus 1 k times. So this is the time. So within this time, one vertex which is started from here, it will try to rotate like this and come back to the same position. So this is the time period of the rotation. That's what actually he asked us to prove. I hope you understood the question. Got it or not? Is there any confusion on the question itself? Now actually, so I will give you 5 minutes time. You try to model this as a complex potential and then try to find out the complex potential at this particular point. So let us say this location is Z, and then this is the horizontal axis X axis, and this is the vertical axis Y axis, and this is a random location of Z. Now this particular vertex, right? So this is at A. Then this is distributed, right? In certain fashion, actually it was distributed. Let us say if we take one first vertex, so this is making an angle of theta, and angle of theta will be, theta is nothing but total 2 pi, and there are n vertices are there. 2 pi by n is the angle theta. Then the complex number which is representing this particular point, the first vertex Z1, actually you can treat as, so A into R e power I 2 pi by n. Got it? So this is the location of this particular point. Now what is the location of this one, the second point? That will be, Z2 will be A into R e power I 2 pi by n times of 2. And then Z3 will be A times of R e power I 3 times of 2 pi by n. So this is how actually all the vertices are located at different locations. Now the total complex potential of this particular point is nothing but W is given by, so Ik by 2 pi times of log Z minus Z1. So first one is log Z plus log Z minus Z1 plus, so this is Z minus here, log Z minus Z2, like this, log Z minus Zn minus 1. Because, so if you start with 1, right, so it will end with n minus 1, then the next one will be the n. Got it? So this is how actually all the vertices are modeled as the complex potential. Now Ik by 2 pi is taken common out, then log Z minus A, Z minus Z1, Z minus Z2, Z minus Z3, like this, actually all the complex potentials are modeled for each of the vertex to have a velocity at the point Z. Got it? Now it is up to you to simplify this one. So this is a simple complex analysis, right? So this complex analysis you need to take it, and then finally you need to separate the real part and the imaginary part, and finally you have to find out the velocity, the complex potential. Actually we have got a beautiful relation, that is, so that is minus u plus iv is equal to dw by dz. So this is one of the very important relation which will simplify our work to a great extent. Got it? So from this, actually we need to identify the velocity. So try to bring the velocity from this, or else actually you can find out the complex potential, that is the real part and imaginary part, you can separate it out from this. So one part will be the scalar potential, another part will be the streamlines. So will you be able to separate this? Try to see if you can separate it. Will you be able to simplify this? Yes. I told you this is the complexity involved in it. Now let me take the action. Now this complex potential, right? So this is A times of R e power I theta. So that is Ik by 2 pi. W is equal to Ik by 2 pi times of log Z minus A. So anyway, in between plus is there, right? So this plus actually Z minus. So A e power I theta. Z minus A e power I 2 theta. Z minus A e power 3 I theta dash 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 Z minus A e power n minus 1 times of I theta. Now this is the complex potential, right? Now if you notice all these values Z minus A power I theta and Z minus A power 2 I theta, Z minus A e power 3 I theta and dash 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 up to n minus 1 I theta, this will be the solutions of Z power n minus A power n is equal to 0 solutions, or Z minus A equal to 0 and Z minus A e power I 2 I theta equal to 0. Now all these things, right? So whatever you see, so all those are nothing but the solutions of this. Got it? So all these are the solutions of this equation. How it is going to, I'll just show that. See this, Z power n is equal to A power n. Z is nothing but A into 1 power 1 by n. So 1 can be written as A times of, so 1 can be written as cos 0 plus I sin 0 or cos 2 pi plus I sin 2 pi whole power 1 by n. So this is A times e power I 2 pi by n. This is Z. For different values of n, you are going to get different values of Z. These are nothing but the solutions of this equation. Z power n minus A power n is equal to 0. So this is how actually you will be modeling it. That means this entire product you can replace with Z power n minus A power n. Got it? Understood or not? So this is just to model or to factorize this. So this is the methodology to factorize. Once we factorize this, so Z power n minus A power n can be treated as the product of all these things. Is this clear? This is one of the very, very important observations you have to make it. Any questions on this? And then once you got to know that, so W is equal to Ik by 2 pi log Z power n minus A power n. So this is the complex potential. Now from this complex potential, we have to identify the velocity. So how do we identify the velocity? How do we identify the velocity? So in the textbook actually he made so complex which you cannot understand. I'll give you a simpler solution for this. So here actually we can identify the velocity q square as dw by dz times dw bar by dz bar. So this is the product of the dw by dz and dw bar by dz bar. So this is also bar and this is also bar. If this is the case, this will give the square of the velocity because dw by dz is nothing but minus u plus iv. Got it? Minus u plus iv. So from this dw bar dz bar is nothing but, so this is minus u minus iv is nothing but dw bar by dz bar. Now the product of these two will be u square plus v square. So that is dw by dz times dw bar by dz bar. The product of this will be u square plus v square is nothing but q square. So this is the velocity. So by making use of this relation, what we can do is, so w bar is nothing but minus ik by 2 pi times of log z bar power n minus a power n. Now the product of these two will be dw by dz into dw bar by dz bar is equal to, so ik by 2 pi. So derivative of this is n into z power n minus 1 divided by z power n minus a power n. Similarly, so the product of this is minus ik by 2 pi times of n into z bar power n minus 1 divided by z bar power n minus a power n. Then this can be further simplified as, so this can be further simplified as ik by 2 pi. So I square will be minus 1, minus into minus will be the plus. Then k by 2 pi whole square. So n into n is n square. So nk by 2 pi whole square. And then the numerator will be z into z bar whole power n minus 1 divided by, so here z into z bar whole power n plus a power 2n minus a power n into z power n plus z bar power n. So this will be nk by 2 pi whole square times of, so z bar. So the product of these two, that is z is equal to x plus iy and z bar equal to x minus iy. So the product of z bar will be x square plus y square, and this is usually we write as r square. So this is r power 2n minus 2, because r square whole power n minus 1. Z bar is anyway r square, so this is r power 2n plus a power 2n minus a power n into, so z power n plus z power minus n. What is the value of that? What is the value of z power n plus z power minus n? Tell me, what is the value of this in terms of r theta? Can you give me in terms of r theta, z power n plus z power minus n? So this value will be 2 times of r power n cos n theta. This is the value of it. I hope you understood that. So r power 2n plus a power 2n minus 2a power n r power n cos n theta. So this is the velocity square. So this is the product of this. So this will be nothing but the q square value. So q square value you can find out from this. From this you can find out the q value by taking the square root of this. So this is the velocity at any point. Got it? You can note down this. I hope everybody understood this. Z power n plus z bar power minus n is equal to 2 times of r power n cos n theta. If not, I am going to explain. First you note down this. Got it? Note it down. Okay. So this is the velocity, whatever we have calculated is the velocity of any fluid particle at any random location, right? So that will give them a random location velocity of a fluid particle. Now actually one more question what he asked was, so with what velocity any vertex is moving? That is one question. And that velocity, right? So whatever the velocity this vertex is moving, so it takes a time period of some value whatever he has given. So to rotate from this point to the again to the same position what after one complete rotation. Got it? So here actually z power n plus z bar power n, z bar power minus n, right? So you know that z is equal to x plus iy, and this can be treated as r e power I theta. Now here it is r e power I theta whole power n plus this z bar will be x minus iy. This can be treated as r e power minus I theta. So this is r e power minus I theta whole power n. So r power n you can take out, and then this is e power I n theta plus e power minus I n theta. So this is nothing but, so e power I theta plus e power minus I theta by 2 is cos theta. So this is cos n theta it will be. If I divide with 2 and multiply with 2, then this will be cos n theta. So 2 r power n cos n theta. So this is how actually we got that. You can note down this. Got it? Okay. Now what is the complex potential at z is equal to a? Let us consider the vertex at point A. Vertex at z is equal to a. Then the complex potential at z is equal to a is nothing but total complex W dash is nothing but total complex potential minus the complex potential of this. Why? Because when we model at any random location z, we have considered all the complex potentials of all the vertices. Now we are modeling at this particular vertex itself. That means this complex potential should not be considered because this fluid particle is not getting influenced by its own vertex. Got it? So that's what we have discussed previously. Now if you subtract that one, this is so ik by 2 pi times log of z minus a. Now this is W dash, but here it is ik by 2 pi times of log of z power n minus a power n minus ik by 2 pi times of log of z minus a is the new complex potential at the vertex. So the complex potential at the vertex z is equal to a. Got it? Now the simplified version of this will be W dash is equal to ik by 2 pi. If you take it out, then this is log of z power n minus a power n minus log of z power z minus a. Now if you separate the real and imaginary parts for this, so psi dash will be the streamlines for this, right? So psi dash is nothing but the streamline equation. At z is equal to a. So at this point we have the streamlines equation. Now the streamline equation, if you wanted to identify here, so here actually z can be treated as x plus iy, right? And here actually x plus iy. Now the real part and imaginary part you can separate it from this, and the imaginary part will be the stream function, but there is one I here. So if you multiply with I, the real part will become imaginary part will become real, right? So you have to use this principle and then get the streamlines is nothing but the real part of this particular one will be the streamline, because usually streamline is the imaginary part, but there is one I here. Got it? So if you multiply that, then you are going to get the streamlines function. So this one you can find out. So here actually, so to find out this one, z you can treat as r e power I theta. Then z power n is equal to r power n e power I n theta. So this is I k by 2 pi log of r power n e power I n theta minus a power n minus log r e power I theta minus a. This is I k by 2 pi. This is still in complex form. Got it? So you note down till this point. Now actually we will simplify this to get the stream function. Got it? So note down this. Done? Okay. Now here, what we have got is W dash is equal to I k by 2 pi times of log r power n e power I n theta. R power n e power I n theta can be written as cos n theta plus I sin n theta minus a power n minus log r into cos theta plus I sin theta minus a. And this will be I k by 2 pi log r power n cos n theta minus a power n plus I times of sin n theta into r power n minus log r cos theta minus a plus I sin theta. Now, if you put it in r dash e power I theta dash format, then this will be, we are interested. So if you write this format r dash and e power I theta dash format, and then from there if you try to separate the real and imaginary part, that will be a little bit complex because you need to identify this data value and this one. But what we are interested is only the stream function, the psi dash. So if you wanted to identify the psi dash, then because there is a multiplication of I, you can identify the real part of this entire equation. So the real part of this entire equation will be, so this square plus this square is the capital R dash square, and here also this square plus this square. So this will be the separate part you can identify. So psi dash will be k by 2 pi times of, then log of, so this is r power n cos n theta minus a power n whole square plus r power n sin n theta whole square minus log of r cos theta minus a whole square plus sin theta whole square. So this is how actually you will separate the real part of this, and from there multiplication of I will be the imaginary part of this. This is nothing but the stream function. Got it? So this, if you further simplify this, k by 2 pi times of, and this will be log of, so square of this. So this will be r power n, r power 2n plus a power 2n minus 2a power n r power n cos n theta minus log of r square plus a square minus 2r a cos theta. So this is the stream function equation of the vertex at this particular point. Got it? Understood or not? Is this understood, or do you have any questions on this simplification? So we are doing only simplification part. So simplification is a little complex. This one here actually we have squared this and added this. Now actually a minus b whole square format, a square r power n cos n theta whole square. Now a square and here r power n sin n theta whole square. So sin square n theta cos square n theta will be 1. And r power n here and r power n here. So if you take it common, then you are going to get r power 2n. Got it? So this is the first one. And then the square of this is a power 2n, I have written. Now a minus b whole square, right? So 2 times of a power n into r power n into cos n theta. So this is the only the, yeah. So I squared it and added it, simplified this. Exactly in the similar manner this one. But how you arrive at this is important. We arrived at this point because of this one. So this is actually involving both real part and imaginary parts, the top one. From that, I have separated the real part of this, which is nothing but the magnitude part. That magnitude, if you multiply with I, it will become the imaginary part. That imaginary part is the stream function for us. That stream function what we have derived now. So this is the stream function equation, psi dash, at the point of this one. So this is where actually we have derived. For that, you need to substitute at z is equal to a. So z is equal to a will become r is equal to a. Got it? So z is equal to a is nothing but r is equal to a because theta is equal to 0. If you substitute theta is equal to 0 in this, if you substitute 0 at this equation, now, so sorry, z is equal to a, z is equal to a in this equation, r will become a. So substitute r in this. Okay, so before substitution, right, we will find out if there is any change d psi by dr and d psi by d theta. Both actually we need to be finding it out. Why we are finding it out here it is, see this is a vertex, and this vertex, now actually this is in a circular format. So all the vertices are distributed in a circular format. Now the stream function we are deriving at this particular point. This stream function, now actually so initially when I discussed the problem statement, I explained one fact. That fact is these vertices are moving, but how they are moving, we don't know that. So to know that, the stream function derivative with respect to r and the derivative with respect to theta, if there is any finite value, then we can know that there will be a movement in that particular direction because there is a change. Now if I take the derivative dou psi by dou r, if I take it, then the streamlines are distributed in the other way. Like actually, so dou psi by dou r with respect to r, if there is a change, then actually the streamlines are, suppose if the streamlines can be this way or the streamlines can be this way, which we don't know. Now we are trying to identify if the streamlines are this way or this way. So if this is the case, so the streamlines are moving like this, that means these vertices move away radially. So for that, it has to be having a derivative with respect to theta. And then if the streamlines are moving like this, then it has to have the derivative with respect to r. Got it? So if dou psi by dou r is a finite value, then the streamlines are in such a manner that this is the way it is distributed. If dou psi by dou theta is finite value, the streamlines are moving in this way. So if both are there, then it will be some random direction. Now we are trying to verify whether these vertices are moving in the circular fashion or not. For that, dou psi by dou r should be having a finite value and dou psi by dou theta should be equal to 0. That's what we are trying to verify it here. Now dou psi by dou r value, if you take it at r is equal to a, so k by 2 pi times of, so 1 by this entire thing, that is r power 2n plus a power 2n minus 2a power n r power n cos n theta. And the derivative of this will be 2n r power 2n minus 1 plus 0 plus 0. So minus 2a power n cos n theta. Derivative of n will be n into r power n minus 1. Got it? And then this is the first part of it. Exactly in the similar manner, derivative of this, the second part, that will be minus 1 by r square plus a square minus 2ar cos theta. And so this derivative will be 2r minus 2a cos theta. For this you need to substitute z is equal to a, because that's what we wanted to find out at this particular point. What is the direction of the stream? Now for this one, if you substitute it, note it down till this point. Okay. So dou psi by dou r at r is equal to a, it will be a simple number. So the simplified format of this will be dou psi by dou r at r is equal to a. This will be k times of n minus 1 times of by 4a. And similarly, dou psi dash by dou theta, if you take it, this will come out to be 0, because in this part, right, so the theta part is going to be vanished out. So dou psi by dou theta, dou psi dash by dou theta value is coming out to be 0. Then we can conclude that this will move in a tangential direction to the circle at that particular point. If you take this one, this will be a tangential direction. So all the vertices are moving in a tangential fashion. Got it? Understood or not? So it will move in a tangential fashion. So if it is moving in a tangential fashion, then that means, so dou psi by dou r will be a finite number, because there are multiple streamlines across this, across r. That's the reason there is a finite number for this. Got it? So dou psi by dou theta equal to 0, because there are no streamlines distributed in the theta direction like this. Got it? So that's why dou psi by dou r is nothing but k times of n minus 1 by 4 pi a. 4 pi a. Yeah. Any questions till this point? Got it? So this will be the velocity of the vertex. This is dou psi dash by dou r will be the velocity of the vertex at z is equal to a. So this is the velocity of the vertex. Now with this velocity, if it is moving tangential, then the time taken for one complete rotation, one complete rotation it will be t is equal to, so total distance it has to travel will be 2 pi r, so 2 pi a. This is the distance by velocity. So with this velocity each vertex is traveling, that is k into n minus 1 by 4 pi a. So if it is moving, then actually this will be 8 pi a by k times of n minus 1. This is the time taken for one circle, one complete rotation. Understood? Understood or not? Do you have any questions on this? Yeah. So this is 2 pi a divided pi square a square. Yeah. So 2 pi a by k times of n minus 1 divided by 4 pi a. This will become 8 pi square a square. Yeah. This is correct. Got it? So this is finished. So to summarize, what is happening is the problem statement, the procedure is simple, but the complexity is only simplifying the procedure. So here, let me explain. Only two important aspects with respect to fluid dynamics we have discussed. Rest of the thing is only complex analysis. So that aspect is, so the problem statement what he has given is, the vertices are distributed in a cylindrical fashion like this. So all the vertices are rotating at respective positions. Now, because of the rotation of one vertex, so this particular vertex, if you consider it, because of all other vertices, this vertex will move, obviously, right? So the fluid particle at this particular point is getting influenced by all other vertices. That means the fluid particle is moving. Now, when it is moving, this is getting influenced by all other vertices, but not the same vertex. This is one important aspect if you are considering a fluid particle within the vertex. But this is not the case if there is any random location from here actually if you select it. So if you select a Z location here, then this fluid particle whichever is present here is getting influenced by all other vertices, all the vertices. So here or here, except for the point at this particular vertex. Yeah, so this is actually, I follow Shanti Swarup, but actually Shanti Swarup is a subset of Rai Singhania. So Rai Singhania actually is covering all the problems, whatever is present in Shanti Swarup, exactly the same problem. Along with that, some other models also it was covered there. But actually whatever I discuss in the class, that is sufficient enough. Got it? So these problems are complex only. You can try other models. Yeah. Okay. So this is one fact. Now actually from this, two different things actually I found. In both the cases actually what he asked is to find out the velocity. That is the one simple question. So if you want to find out the velocity at any point, so at any random direction here, so this location, the velocity is, we always have the relation dw by dz is equal to minus u plus iv. This is one relation. And then from this actually, so the way in the textbook he derived is dw by dz actually is equal to minus u plus iv, but he opted a different approach. So he separated the real and imaginary parts, and then so from the complex potential. So W is equal to the complex potential of all the vertices at this particular point is nothing but Ik by 2 pi times of log of z minus z1, z minus z2, z minus z3 up to z minus zn, zn minus 1. So for each point actually you can model in terms of A and 2 pi by n. Because this is in a circular fashion, you can put it in theta format. So that's what is the big complex potential what you are going to get it, which is nothing but z minus a into z minus a e power I theta into z minus a e power 2 I theta into a e power z minus 3 I theta, like this up to z minus a e power I n minus 1 theta. Now all this nothing but the solutions of z minus z power n minus a power n is equal to 0. That means all the factors together we can conclude as a simple single equation, that is log of z power n minus a power n. That is one important conclusion. So which is nothing but a complex potential at any random location selected except on this particular circle. Now from there actually we found the velocity. For that velocity there are two approaches you can adopt. So now we are using the polar coordinates. So that's why that z power n minus a power n, put it in the real and imaginary part and separate the real part and the imaginary part. And the imaginary part is nothing but the stream function psi. Now dou psi by dou r is nothing but the velocity of the fluid. So dou psi by dou r in polar coordinates. So that way you can separate the real and imaginary part, find out the stream function as psi, and take the derivative of this dou psi by dou r. It is going to give the velocity. That is one method that is very complex. But rather than that, I found an easy approach, that is dw by dz into dw bar by dz bar. If you multiply these two, that will give in one line, entire complexity will go for a toss. So it will give in one line the velocity square value, q square value. So that way you can find out the velocity of this fluid particle randomly it was selected. This is one part of the problem statement. The second part of the problem statement is the vertex whichever is present here is now moving. The movement with what velocity it is moving, in what direction it is moving. That's what is the first question. So that part what we can solve is, so for this particular point, we found the complex potential again because the complex potential at this point and at this point is different because this is on the circle where the vertex is present there. So if the vertex is present, then that fluid particle is getting protected by this own vertex. So this is getting influenced by all other vertices. Now if it has to move that particle, it has to move the vertex like that. Now if it is moving the vertex, right? So the complex potential that needs to be considered is because of all other vertices except that. So that's why we have subtracted the complex potential of this particular part from the total complex potential. And from there, we have adapted the approach of, that is, finding out the streamlines. And the streamlines, we have taken the derivative of it is nothing but the velocity, the tangential velocity that will be given dou psi by dou r value. So that's what we found by separating the psi value. So once we identify the imaginary part of the other complex potential, what we found now. So from there actually, what we have taken is, at this particular point, we have taken the derivative of it at z is equal to a. Then the derivative with respect to r and with respect to theta we have found separately so that we can find out the tangential velocity and the radial velocity. But it was coming out to be only the tangential velocity is there and no radial velocity is there. So that's why the radial velocity is treated as 0. That means if there is only tangential velocity, we can conclude that this vertex is moving in a circular fashion. At any point it is tangential. So it is moving in a circular fashion. Now the second question what he asked was, if it is moving in the circular fashion, then what is the time taken from this point to come back to the same position after one complete rotation? And that time actually you can find out once you find the velocity of this, the same way what we found in the previous case. So once we find the velocity of it, then take the ratio of distance by time. Distance is 2 pi a and the time is whatever we calculated. So time is nothing but the velocity. So velocity, if you divide it, then you are going to get the time. So this time is coming out to be 8 pi square a square by k times of n minus 1. Got it? Any questions on this? Got it? Okay, so that's all for today. Yeah, thank you. Yeah, good night. Bye bye.